Hi guys, in the last lecture I introduced to you the concept of single phase induction motor. In this we saw there were two rotating magnetic field. One was forward, other was backward. And under standstill condition when slip was 1, flux of forward was equal to flux of backward, due to which torque of forward was equal to torque of backward and net torque was 0. So the single phase induction motor is not self-starting. So what we did is we introduced the auxiliary winding. We introduced the winding such that X by R ratio of auxiliary winding is less than X by R ratio of main winding. And we called it as the resistance start induction motor or resistance start single phase induction motor because of the resistance of the auxiliary winding. Here we did not use any capacitor, so the cost was low. Okay. So now in this lecture we will study about more starting methods or more modifications to the design of single phase induction motor to improve the starting characteristics. Now the concept of capacitor type of motor is introduced. So what happens is, in case of auxiliary winding we saw this was my voltage phasor, this is my auxiliary winding current, this is the main winding current. Suppose there is an angle alpha between them. Now the torque produced by the machine is proportional to sine of angle between the two currents. Torque is proportional to sine alpha. So to increase torque, we must increase alpha. And for maximum torque, alpha should be 90 degree. That means auxiliary winding current should be like this, at 90 degree to the main winding current. But for that the auxiliary winding current must be leading the voltage, and for leading we need a capacitor. That is why we introduce a capacitor in series with the auxiliary winding to make the auxiliary winding current leading, so that we can have a 90-degree phase shift between the currents of main winding and the auxiliary winding to increase the starting torque. So suppose the capacitor of Xc reactance is introduced. So the net impedance of auxiliary winding will be Ra plus Jxa minus Jxc, because now auxiliary winding will be something like this. It will be Ra, Jxa and minus Jxc. This will be the impedance of auxiliary winding. Impedance of main will be Rm plus Jxm. So this angle of the main winding, let us call it as phi m, and angle of the auxiliary winding. Okay, so how it will be? This phi m will be tan inverse xm by Rm. Okay, and since it is lagging, so we can keep it minus, or let us keep it as it is. Phi a is leading, so I will write it as tan inverse xc minus xa by Ra. Why I am writing xc minus xa? Because it is leading, that means xc is greater than xa. So that is why I am writing xc minus xa. So here I have written the angle such that both the angles will come out to be positive. So that is why I am just only considering the magnitude of the angles. Now from the figure what I can say is, sum of both the angles will be 90 degree. That means phi m plus phi a will be 90 degree. So tan inverse xm by Rm plus tan inverse xc minus xa by Ra should be 90. So we can take tan inverse xm by Rm on the right hand side. Okay, So 90 minus tan inverse xm by rm will be tan inverse xc minus xa by ra will become tan inverse rm by xm, because tan of 90 minus theta is cot theta, so cot theta is reciprocal of tan theta. That means xc minus xa by ra will be equal to rm by xm, or we can say xc will be equal to xa plus rm ra by xm. Okay, once we find the value of xc, we can find out the value of capacitance. How we can determine the value of capacitance? Capacitance will be 1 by omega xc. Okay, so that is how we can find the value of capacitance required to make both the currents at 90 degree, so that we can have the maximum starting torque. Okay, so the first category of capacitor type of motor is capacitor start motor. Here capacitor is connected in series with auxiliary winding, but it is connected in series with a centrifugal switch also. Now due to this centrifugal switch, when speed is almost 75% of ns, capacitor becomes disconnected. So the capacitor is only used to start the induction motor, and it will be disconnected during the running condition. So it is not present in the running condition of the motor. And here the cross sectional area of auxiliary winding is 50% of main winding. Why? Because here we do not need to keep a x by r ratio high. That is not a necessary requirement, because the phase shift will be provided by the capacitor. Earlier only x by r ratio was available to us, so we have to make the phase shift as large as possible just by altering the x by r ratio of the windings. But here mostly the phase shift is due to the capacitor, so we do not need to focus on x by r ratio, rather the capacitor will provide the additional phase shift. Okay, that's why it is not necessary to keep the auxiliary winding cross section at 25%. We can keep it higher, and the higher cross sectional area allows us to have a higher current rating. Current rating is always proportional to the cross sectional area of the winding. Now how will the torque slip characteristics look like? First we will draw for the normal induction motor, that is due to the main winding, and then due to capacitor start, how it will be? Starting torque will be very high, and once it is disconnected, the windings, the characteristic will be as same as main. So this is due to capacitor start. So if you see now, starting torque is higher as compared to the previous case with only auxiliary winding. So that is how the starting torque increases when we use a capacitor. Here the centrifugal switch is operating. Okay, so in capacitor start motor, what we learned is the value of capacitance required is 1 by omega xc, and xc is xa plus ra rm by xm. So do remember this formula, or do remember the concept how we derived this. So this will create a 90 degree phase shift, which will provide us the maximum torque. So that way we will have the maximum torque at starting. Okay, so this formula is very important, as most of the numericals are framed or based on this concept only. Next is the capacitor run motor. Here if you see, the capacitor is permanently connected to the induction motor. So that is why capacitor connected will provide a phase shift between the auxiliary and the main winding currents, which will cause a rotating magnetic field to be set up, and it will cause a smoother torque. So it has a more smooth or a smoother torque. Due to smoother torque, what will happen is noise is less and there are lesser vibrations. So that is the advantage of having a capacitor even under running conditions of the motor. So the torque slip characteristics will be something like this. Here we will have some starting torque and it will be same as that of a three-phase induction motor. And this motor is silent in operation. In case of capacitor start, what was happening? The starting torque was very high, but under running condition the operation will be noisy and vibrational because it goes back to the original condition where we had only the main winding. Okay, that is why the operation is noisy and vibrational. Next is your capacitor start and capacitor run motor. Here we have two capacitors, one is used for starting and other is connected during the running condition. So this capacitor remains permanently connected and this gets disconnected during the running condition. So what will happen is, how will the torque slip characteristics look like? Due to running capacitor, characteristics will be something like this. And due to this starting capacitor, what will happen? The characteristics will be high. Then they will go back to like this. So the advantage here, since two capacitors are being used, so the operation will be costly. But due to run capacitor, the operation is silent and non-vibrational. Okay. So run capacitor will improve the running characteristic and start capacitor will provide a higher starting torque to the motor. So these are the basic type of modifications that we do for a single phase induction motor. So you must remember the torque slip characteristics of each of these modifications as that is important for the gate examination. Next, let us look a bit about the universal motor. Let us take a look what is a universal motor. As the name suggests, it is universal, that is, it can operate at both AC and DC. So basically in DC there are two type of machine, shunt and series. I am talking about self-excited. So what happens in case of shunt? If we provide an alternating current, but the field winding current will be DC and torque is proportional to IF into IA. So what will happen? Due to IA being alternating, the torque will be alternating. So the torque will be like this. It will be positive for one half cycle and negative for other half cycle. So the motor will rotate in one direction for one half cycle and in the other direction in the other half cycle. But the motor has certain inertia, so it cannot quickly change its direction. That is, the motor will vibrate and it will not be able to rotate. So DC shunt machine can never operate in case of AC supply. But in case of series, what will happen if armature current is AC? Armature current is also equal to field current. Torque is proportional to IF into IA square. So torque will be pulsating, but it will be unidirectional. Since the torque is unidirectional, the motor will rotate in a single direction. Such a motor is called as universal motor. So DC series motor can run at AC also, and it is called as universal motor. But here, since we are running on AC, we need to consider the armature inductance or armature reactance also. So there will be some voltage drop due to reactance, and thus the EMF will be slightly lesser as compared to DC. In case of DC, the voltage drop was only due to RA, but here voltage drop is due to RA as well as XA. So the model of this machine will be this is VT angle 0, armature resistance, armature reactance, and this is EMF. Now due to RA and XA, the voltage drop will be higher and EMF will be lesser. Okay, so that is how we operate a universal motor. Let us take a look at the problem based on single phase induction motor. For a single phase capacitor start, that is, the capacitor is connected only at the start, induction motor, which of the following statement is valid? Capacitor is used for power factor improvement. No, capacitor is used to improve the starting characteristics. Direction of rotation can be changed by reversing the main winding terminals. Direction of rotation cannot be changed. It can be changed by interchanging the supply terminals. Now remember, the torque will be proportional to Im, Ia and sine of angle between them. So if you reverse any one of the current, then the torque direction can be reversed. So either you reverse the main winding current or you reverse the main auxiliary winding current. Or you can understand, if you reverse the auxiliary winding or the main winding MMF or the magnetic field, then the torque can be reversed. But if you change the supply terminals, that is, I am reversing the supply, the same voltage is connected across the auxiliary and the same voltage is connected across main. So both main and the auxiliary currents will be reversed, or main and auxiliary magnetic field will be reversed. Since both are reversed, net effect will be the same direction of rotation. So this operation is incorrect. This option cannot be correct. Why? Because the direction of rotation will remain same in case both the things are reversed. But if you change only the main winding terminals, then main winding flux will reverse and the auxiliary winding flux will remain in the same direction. That is why the direction of rotation will be changed. Hence the correct option is B. Okay. So remember this concept, torque is proportional to Im into Ia into sine alpha. Let us look at another problem. It is saying a single phase 230 volt 50 Hz 4 pole capacitor start induction motor has the following standstill impedance 6 plus J4 8 plus J6. We need to find the starting capacitor required to produce 90-degree phase difference between the currents in main and auxiliary winding. Okay, so we saw that Xc for 90-degree phase shift was Xa plus Ra Rm by Xm. Reactance of auxiliary winding is 6, Ra is 8, Rm is 6 by 4. So it will be 18 ohm. Now capacitance will be 1 by omega Xc 1 by 2 pi into 50 into 18. So it comes out to be 176.83 microfarad. Okay. So that is the capacitance required to produce a 90-degree phase shift between the main and auxiliary winding current to have the maximum torque produced by the motor. Moving on to our next problem, it is saying a 200 volt 50 Hz single phase induction motor has the following connection diagram. MM dash is the main winding orientation, AA dash is for the auxiliary winding. Direction of windings axis indicate the direction of flux when currents are produced. Parameters of each winding is indicated. When switch is closed, the motor will. Okay. So when we close the switch, we need to find the direction of rotation of the motor. So let us first find the reactances. Xa, it will be omega La, that is 2 pi into 50. La is given to be 10 by pi. So it will be 1000 ohm. Similarly, Xm will be omega Lm 2 into pi into 50 into 0.1 by pi. Okay. So it will be how much? It will be, this will come out to be, Xm will be 10 ohm. Okay. This is 1000 and Xm is 10. Now we know the torque depends on the sine of angle between the currents. So let us first find the angle of auxiliary winding. Tan inverse Xa by Ra. Tan inverse 1000 by 1. It comes out to be 89.942 degree. Similarly, tan inverse Xm by Rm. Tan inverse 10 by 0.1. So that is tan inverse 100. It comes out to be 89.427. So torque is proportional to sine of 89.942 minus 89.427. So it is proportional to 0.009, which is very small. So this torque may not be greater than the load torque, and hence this induction motor cannot be started. Okay, so it does not rotate. Okay, because the torque is coming very small, the currents are almost in the same phase, and we need a larger phase shift to produce a significant amount of torque to rotate the motor. This torque may not be able to overcome the inertia required to rotate the motor. It may not be able to overcome the frictional or the damping forces inside the machine. So let us summarize what we learned in this lecture. We first saw why capacitor is required, and we determined the value of capacitance for having the 90-degree phase shift between main and auxiliary winding. Then we saw capacitor start characteristic, which had a higher starting torque, but operation will be noisy and vibrational because capacitor is disconnected after a certain time. Then we saw capacitor run motor, in which capacitor is permanently connected, so we have a smoother operation. Then we saw capacitance start and capacitor run, which combines the advantage of both, but it is more costly. Then we saw universal motor, that is a DC series motor which can be run on AC. That is the universal motor. So this is all about the single phase induction machine. Okay, so the only important concepts here are characteristics of the capacitor type of induction motor and the value of capacitance to produce a 90-degree phase shift between main and auxiliary winding currents.